Okay, I guess we can begin, and people can join. So we're very happy to have Martin Taylor with us today. So Martin is a mathematician. He's a Royal Society University Fellow at Imperial College, London. He received his PhD from the University of Cambridge, and his research interests are in analysis of partial differential equations and general relativity. So today, he's gonna tell us about the nonlinear stability of Schwarzschild. So full nonlinear stability of Schwarzschild. There was a 500 plus page paper posted on Monday. So if you didn't get the chance to read it, now is your opportunity to get a head start. We're very happy to have Martin. You can take it away.
Okay, thank you very much, and thank you very much for the invitation. It's a pleasure to be able to speak at the Black Hole Initiative, and I just hope before long we're able to do this in person again. So everything I'll say is joint work with Michalis Stathemos, Gustav Holzegel, and Igor Rodniansky. And as you say, this work appeared on the archive yesterday, or I guess it was Sunday evening if you're in Boston. And so if you get impatient during the talk, you can open the paper and read it. So I don't want to explain the entire proof. I just want to explain some of the key difficulties which arise in this problem. And in fact, the reason this is true, the reason Schwarzschild is stable, relies a lot on some very special properties of Schwarzschild and of the Einstein equations. And so I would just like to emphasize these special properties in the talk. So I'll begin by reminding you of some of the basic properties of the Schwarzschild family and reminding you what its stability means. Then there are nonlinear difficulties which arise in this problem. Some of those nonlinear difficulties arise already in the stability of a simpler solution, namely Minkowski space. So I'll very briefly summarize the most important aspects of that problem. Then many of the new difficulties are linear, and in fact, many of them arise already in what can appropriately be called the poor man's linear stability problem of Schwarzschild. So I'll very briefly talk about this, then I'll discuss how to go from poor man's linear stability to linear stability. And if there's time at the end, then I'll discuss some of the new nonlinear difficulties which are specific to this problem. So I prepared quite a lot, so I'm not sure if we'll get to this last point or not. So Schwarzschild is the most famous family of solutions of the vacuum Einstein equations. It's a one-parameter family discovered in 1915, and each member describes a static black hole, and this parameter m has the interpretation of the mass of that black hole. So as we all know well, there's an exterior region which is complete, meaning that observers can live forever in the exterior, or more precisely, there's an asymptotic boundary which can be attached future null infinity, which is future affine complete, and the black hole exterior is characterized as the past, the causal past of this asymptotic boundary. So the exterior is bounded to the future by an event horizon at r equals 2m, and observers can remain in the exterior for all time and are causally unaffected by what happens beyond the event horizon. So this is particularly convenient for us since it means we can understand stability properties of the exterior without worrying about what goes on in the interior, where in fact instabilities are expected. So it's convenient to view Schwarzschild as dynamically as the Cauchy evolution of two-ended Schwarzschild initial data. So if one considers a two-ended asymptotically flat space-like hypersurface in Schwarzschild as depicted, and one looks at the induced metric and second fundamental form on this hypersurface, then the Cauchy evolution of this initial data set is exactly the Schwarzschild solution. And so it's convenient to think of Schwarzschild this way. So then the most fundamental question we can ask about Schwarzschild is this exterior region non-linearly stable as a solution of the vacuum Einstein equations? So of course, this has nothing to do with the two-ended nature of Schwarzschild. And in fact, the problem localizes completely to one of those two ends. And in fact, it's convenient to localize the problem further to what's called a characteristic initial value problem. So instead of considering initial data on some space-like hypersurface, one considers two transversely intersecting null hypersurfaces, one of which extends to infinity, and the other which crosses the event horizon. So there are three types of stability question we would like to understand. So if one considers such induced Schwarzschild data, perturbs it slightly, then we would like to know in the corresponding Cauchy evolution, can observers still live forever in the exterior, like was the case in Schwarzschild? And of course, this question goes by the name of the weak cosmic censorship conjecture, specialized to a neighborhood of Schwarzschild. The second question that we can ask is, do the solutions remain close to Schwarzschild in this exterior region? So this question is known as the question of orbital stability. And finally, we can ask whether the perturbations converge back to a member of the Schwarzschild family. So this third question is called the question of asymptotic stability. So it would of course be of interest to understand any one of these three questions on their own. However, due to the strong nonlinear nature of the Einstein equations, we in fact don't have a way of understanding any one of these three questions without in fact understanding all three of them at the same time. So the three questions, they come as a package. So the first version of the theorem I'd like to discuss, again, this is joint with Dafermas, Hosagel, and Rudniansky. So the theorem says the answer to these three questions is yes. So Schwarzschild is asymptotically stable as a solution of the fully nonlinear vacuum Einstein equations without any symmetry assumptions in the black hole exterior. So if you have any familiarity with this subject, you'll know that there's only one way this theorem can possibly be true, and it's if I mean the question modulo Kerr. Okay, so Kerr, as is well known, is a larger two-parameter family of stationary solutions, which admits the Schwarzschild family as a one-parameter subfamily. So the Kerr family is more complicated and accordingly was only discovered much later in 1963 by Roy Kerr. So there's a mass parameter m again, but now there's also the angular momentum parameter a. So since Schwarzschild is a one-parameter family and Kerr is a two-parameter family, it's tempting to view Schwarzschild as being codimension 1 inside Kerr. However, it's actually more convenient to over-parameterize, in which case Schwarzschild is not codimension 1 inside Kerr, but is codimension 3 inside Kerr. So you should think, if you take a Schwarzschild solution, a member of the Schwarzschild family, and you would like to describe a nearby member of the Kerr family with the same mass, one not only has to specify an angular momentum, but one also has to specify an axis around which the Kerr black hole is rotating. So the angular momentum and the axis is 3 parameters, and so we view Schwarzschild as being codimension 3 inside Kerr rather than codimension 1. So in particular, Kerr with very small rotation is a small perturbation of Schwarzschild, and Kerr is stationary, so it certainly doesn't converge back to Schwarzschild. So in particular, this third question, the answer is no. So when I say stability of Schwarzschild, what I really mean is full finite codimension nonlinear stability of Schwarzschild, or in other words, stability of Schwarzschild modulo Kerr. So the theorem can more precisely be stated as follows. So consider some data close to Schwarzschild with some mass m initial, which moreover lies on a codimension 3 submanifold of the space of initial data. So again, this number 3 is because we view Schwarzschild as being codimension 3 inside Kerr. And you should think that any initial data which does not lie on this codimension 3 submanifold will evolve, the resulting solution will evolve not to Schwarzschild, but to a member of the Kerr family with non-zero rotation parameter. So it's in this sense that this is the full finite codimension nonlinear stability of Schwarzschild. And I put the word submanifold in quotation marks because it's a codimension 3 submanifold from the point of view of counting, but it takes some more work to say anything about the manifold properties of this space, the smooth manifold properties of this space. So for any such data, like Schwarzschild, the solution possesses a complete future null infinity whose causal past is bounded to the future by a complete event horizon. It remains close to Schwarzschild in the exterior, and moreover, it decays at an inverse polynomial rate to another member of the Schwarzschild with mass m final, which is close to m initial. So again, the first of these 3 points is exactly the statement of weak cosmic censorship. The second is the statement of orbital stability of Schwarzschild. And the third is the statement of asymptotic stability of Schwarzschild, all restricted to this codimension 3 submanifold. So there's been a tremendous number of relevant previous works. I'll mention some of them gradually through the talk, but unfortunately I don't have time to mention everything. So first there's nonlinear stability of Schwarzschild, which I will discuss in, nonlinear stability of Minkowski space, which I will say a few more words about in a moment. And without symmetry assumptions, when lambda is equal to 0, this is actually the first nonlinear stability result of a space-time without any symmetry assumptions. So there's been a number of works in symmetries. The simplest symmetry assumptions are those which reduce the problem to something 1 + 1 dimensional. And indeed, there's a very, very big conceptual simplification arising from a 1 + 1 dimensional reduction. So there's been some works in 1 + 1 dimensions on 1 + 1 dimensional problems. Beyond 1 + 1 dimensional reductions, the problem becomes considerably more involved and is in fact there's no conceptual simplification, and like there is in the 1 + 1 case. And the problem is the difficulties are closer to the difficulties of this theorem. So there's a very nice recent work of Kleinem and Jeftel on stability of Schwarzschild in polarized axisymmetry. There are also some works with positive cosmological constant. For example, a few years ago, shown by Hinz and Vashi in a very nice work that the Kerr de Sitter, the very slowly rotating Kerr de Sitter solutions are non-linearly stable. So before I go on, there's a few remarks I'd like to make, and there's a few difficulties which can be preempted already at this stage. So first, the proof is based on a proof of linear stability of Schwarzschild of Dafermas, Holzigel, Rodniansky. So you should think in this type of problem, the relevant linear analysis to base an approach to the problem on is not that of the space-time which you perturb, but that of the space-time which the solution converges to. And so the main reason for this restriction to solutions which converge to Schwarzschild is that these are exactly all of the perturbations which can be understood using a linear analysis around Schwarzschild, as opposed to around Kerr with some non-zero angular momentum. So in particular, this means the proof can be based entirely in physical space. The proof is based on a double null gauge. So a double null gauge means two coordinate functions uv, whose level hypersurfaces are outgoing and incoming null hypersurfaces, null cones respectively, and they intersect in space like two spheres. So I wrote Schwarzschild on the first slides in the more familiar TR coordinates. However, one can also write Schwarzschild in this Eddington-Finkelstein double null form. So here now the R is some function of is a function of U and V. However, one already sees here a fact which complicates the analysis quite considerably. So this is by far not the only way to express Schwarzschild in double null form. So in fact, there's an entire infinite dimensional family of double null gauges even in Schwarzschild itself. And as I say, this fact complicates the analysis quite considerably, and I'll return to it momentarily. So another difficulty is the fact that the black hole exterior is only characterized teleologically. So by this, I mean, recall the black hole exterior is characterized as being the past of the causal past of future null infinity. A priori, one doesn't even have a future null infinity. And remember, I'm not saying anything about the black hole interior. I'm only saying something about the exterior. So not only is the solution an unknown in this problem, but moreover, the region on which the solution lives, the black hole exterior, this is also an unknown in the problem. So moreover, the double null gauge in which the decay to Schwarzschild happens is also teleologically normalized. So in fact, there are two double null gauges in the proof, not one, and they're normalized both to the event horizon and to future null infinity. So again, these things are unknowns in the problem. So the double null gauge in which one has decay to Schwarzschild, that itself depends on how the solution behaves in evolution. So the double null gauge or the double null gauges are also unknowns in the problem. So the fact that the gauge is normalized to future null infinity has this bonus property, which is it's Bondi normalized, meaning that future null infinity is affinely parametrized. And so as a bonus, this means a posteriori, it's very easy to understand many of the familiar laws of gravitational radiation. And in fact, there are even nonlinear effects, nonlinear effects which can be readily understood, such as the nonlinear Christodoulou memory effect. So the final difficulty that I'd like to describe at this stage is the fact that this codimension 3 submanifold is also teleologically characterized. So remember, everything which lies on this codimension 3 submanifold, it contains exactly the amount of angular momentum which it will radiate in evolution. And in general, there is no way to determine how much angular momentum a solution is going to radiate until you start solving and see. So the solution's an unknown, the region's an unknown, the gauges are unknown, and in fact, the initial data that we consider is also an unknown, and that's also constructed as part of the proof. So, whilst in general, the submanifold is characterized teleologically, there are explicit infinite codimension subfamilies which can be described explicitly. So, for example, the vacuum Einstein equations have this property that they do not radiate angular momentum in axisymmetry. So this means if one considers initial data, or if one considers a perturbation of Schwarzschild, which is axisymmetric and moreover has vanishing angular momentum, then necessarily this will lie on this submanifold. So, as an easy corollary of this theorem, one can infer that the axisymmetric initial data sets with vanishing angular momentum are contained in this submanifold. Okay, so I'd like to just say a few words now about stability of Minkowski space. So the fact that Minkowski space is non-linearly stable, you should actually view that as a surprise. So I think this is maybe not so well known outside of the mathematics community. So I'd like to just say a few words about why you should think that stability of Minkowski space at the nonlinear level is a surprising fact. And of course, the difficulties which arise here arise again around Schwarzschild. So in some sense, there's not a lot to say about linear stability of Minkowski space. So for example, if you consider Einstein equations in the harmonic gauge, linearize them around Minkowski space, you'll see that the perturbations satisfy the standard linear wave equation, which is one of the most classically studied partial differential equations. And you can show whatever you want for this. So there's a mode stability statement. There are no finite energy growing mode solutions. You can of course show much more. There's a boundedness statement. So solutions to this equation remain bounded for all time. You can even show decay with a quantitative rate. And the rate at which solutions decay gets faster the higher the number of spatial dimensions is. In 3+1 dimensions, the solutions to this linear wave equation decay exactly at this critical rate of 1/t. Okay, I say critical because 1/t cannot be integrated globally in time. So you should think that this problem is critical to 3+1 dimensions. So Minkowski space is stable. This is a theorem of Christodoulou-Kleinemann from the early 90s. So you should think this theorem, the analog of this theorem for the typical equation, which takes the same form as the vacuum Einstein equations, is completely false. For example, there's a very physical example, which is the compressible Euler equations. So in the irrotational regime, the compressible Euler equations take the form of a system of nonlinear wave equations. And shock waves can form, so they linearize to the standard linear wave equation, and shock wave singularities can actually form in finite time for arbitrarily small perturbations of the trivial solution. So this is typical. So the only reason that Minkowski space is stable is because there's some incredibly special property of the nonlinearity in the vacuum Einstein equations. So this property is called the null condition. It was introduced by Kleinemann in the 80s. And so the Christodoulou-Kleinemann proof involves introducing a geometric gauge, which is not so dissimilar from double null gauge. And some form of null condition is manifest in this gauge, and the proof involves exploiting this heavily. And it's interesting to note that so gauges like double null or the gauge of Christodoulou-Kleinemann, they typically involve some form of renormalization of that residual freedom, depending on how the solution behaves in evolution. So this indeed is already the case there in stability of Minkowski space. Okay, let me now talk about the poor man's linear problem of Schwarzschild. So in some sense, the linear wave equation on Minkowski space is the linearization of Einstein equations around Minkowski space. The same is not true for Schwarzschild. If you linearize vacuum Einstein equations around Schwarzschild, you get a more complicated system. However, it is appropriate to view the linear wave equation on a fixed Schwarzschild background as a poor man's linearization of the Einstein equations. So then the poor man's linear stability problem is the problem of showing that solutions to this equation are bounded and decay in time with quantitative rates. And in fact, one sees a lot of the difficulties already in this poor man's problem. So this has been very, very well studied in recent years. So there are many works, beginning with the work of Reggie Wheeler from 1957, which was in fact on the linearized equations about mode analysis. The first work which did not involve a restriction to fixed modes is a work of Wald from 1979. In recent years, this has been there've been many works. Now we have a complete understanding of this problem, not just for Schwarzschild, but in fact for the full subextremal Kerr range. There is one very interesting open problem left, which is to understand what happens in the case of extremal Kerr. And we know that solutions will at the very least be subject to the Aretakis instability. So a key step in this problem of showing decay of solutions to this linear equation on Schwarzschild is a quantitative understanding of three geometric properties of Schwarzschild. So the first is the celebrated redshift effect. So if so there's a conserved energy for this equation. That conserved energy is not coercive. It becomes degenerate close to the event horizon. And if the only thing you know is conservation of that degenerate energy, that's completely consistent with solutions blowing up along the event horizon. And in fact, this is exactly what happens in the case of extremal rise at Nordstrom, for example. So to overcome this To overcome this degeneration, one has to exploit an additional property of Schwarzschild, and the most robust property to exploit is the redshift effect. So if an observer crosses an observer A crosses the event horizon of Schwarzschild and sends signals to an observer B who crosses the event horizon at some later affine time, later advanced time, the signals, when received by B, will be exponentially shifted to the red. And so this redshift property has a stabilizing effect on waves, and this can be quantitatively captured to overcome that degeneration. The second property is that of trapped null GD6. So as is well known in Schwarzschild, there are null GD6 which neither cross the event horizon nor escape to infinity, but orbit the black hole for all time at the photon sphere at r equals 3m. And so, since waves can localize along around null GD6 for arbitrarily long times, the existence of such trapped null GD6 is an obstruction to decay, is a potential obstruction to decay of waves. And these null GD6 in Schwarzschild are unstable in the sense that if one takes a trap direction, perturbs it slightly, then generically the resulting null GD6 will either escape to infinity or cross the event horizon. And so any proof of decay has to capture that unstable property of these null GD6. So the third is the phenomena of superradiance, and since that's only relevant for Kerr, not for Schwarzschild, let me skip the discussion of that and go straight to the linear stability problem. So that was Pohlmann's linear stability. Linear stability is a little bit less clean to formulate, but let me try nonetheless. And remember, I always have an eye here on the nonlinear problem. So to formulate the problem of linear stability of Schwarzschild, one would first pick a gauge in which the vacuum Einstein equations reduce to a well-posed system, such as double null gauge, for example. One would linearize this reduced system around Schwarzschild. Then the first problem is to show that solutions to this linearized system remain bounded in the exterior. So this is the linear analog of the statement of orbital stability. Then we would like to show that the solutions all decay to this, solutions to this linearized system decay. So this is the statement of the linear analog of the statement of asymptotic stability. However, particularly with gauges like double null, one can only show this after renormalizing that residual double null freedom to account for how the solution behaves in evolution. So if necessary, one has to renormalize this residual gauge freedom for this latter property. And finally, just decay on its own is not enough, as we saw from the linear analog, the linear problem around Minkowski space. One has to make sure that that decay is sufficiently fast. So again, this has been this problem has been very, very well studied, beginning in even in the 50s with that work of Reggie Wheeler. And let me not describe all of these in detail, but I'll just discuss this proof of linear stability of Schwarzschild of Dafermos, Holzigel-Rodniansky. So in double null gauge, recall double null gauge means these UV coordinates whose level hypersurfaces are incoming and outgoing null cones. So associated to a double null, such a double null foliation is a double null frame. And one can look at the Ricci coefficients of this double null frame. So there's some standard notation, and I've added the ones here for their linearized counterparts. So the Ricci coefficients satisfy a system of structure equations. So the Einstein equations, the vacuum Einstein equations can be captured in the form of the structure equations of these null Ricci coefficients. And they couple to the null components of the curvature tensor. And again, there's some standard notation. Again, I've added the ones to describe the linearized counterparts. So the content of the vacuum Einstein equations for the linearized, for the curvature components, can be captured through the so-called null-Bianchi equations. So this is very similar to the Newman-Penrose formalism, if you're familiar with that. So the linearized system one gets for this system of unknowns takes the following form. So the first 2 pages are exactly the linearized structure equations, and the final page is the linearized null-Bianchi equations for the curvature components. So of course you don't have to remember these. If you see them for the first time, then they can look quite long, but I claim they're actually not so bad. So there are 2 special families of solutions to this linear system. There's an infinite dimensional family of what I call residual pure gauge solutions. So these are solutions which arise from this infinite dimensional freedom of renormalizing the double null gauge at the nonlinear level. And then there's a 4-dimensional family of linearized Kerr solutions, which arise due to the fact that due to the presence of Kerr there at the nonlinear level. And this family can be subdivided into a 1-dimensional family of linearized Schwarzschild solutions. And this family is supported only on L equals 0 spherical harmonics. And a 3-dimensional family of fixed mass linearized Kerr solutions, which are supported only on L equals 1 spherical harmonics. And again, the number 3 is the same as before, because one has to specify an angular momentum parameter and also an axis of rotation. So in 2016, it was shown by Dafemos, Hosegal-Roniansky that Schwarzschild is linearly stable. So more precisely, the linearized Kerr solution is stable as a solution to the equations linearized around Schwarzschild. So for all data for the linearized equations, the resulting solution remains bounded in the exterior. So this is the linear analog of orbital stability. Moreover, after renormalizing, this residual gauge freedom decays an inverse polynomial rate to a member of the linearized Kerr family. And finally, this residual pure gauge solution is itself quantitatively controlled. And the nonlinear analog of this statement is very important in the nonlinear proof. So there's an easy corollary of this theorem, which is there is a codimension 3 subspace of initial data for which the solution decays to a linearized Schwarzschild solution, as opposed to a linearized Kerr solution with non-zero angular momentum. So this corollary is what you should compare to the nonlinear theorem. So as I say, one has to renormalize this residual freedom as in the nonlinear problem. However, there are some linear simplifications which are new difficulties in the nonlinear case. For example, the linear analog of the location of the event horizon is explicitly determined in this linearized setting. Moreover, one can also say a priori which member of Kerr the solution will decay to. Okay, so these two facts are not teleological in linear theory. Okay, let me skip this maybe. So I'll just say a few brief words about how this linear proof goes. Then I'll just very briefly discuss I'll very briefly re-emphasize the nonlinear difficulties, and then I'll end. So the starting point of the analysis is that huge linearized system. A convenient place to start is these two quantities called alpha and alpha bar, which are gauge invariant. So if you're familiar with Newman-Penrose formalism, these are usually called psi0 and psi4. And it was noted first by Bardeen Press in the case of Schwarzschild that these two linearized quantities decouple from the rest of the linear system. And this was generalized to Kerr by Minkowski. So these quantities, the linearized equation, the decoupled equation which they satisfy takes the following form. So it's a wave equation, and it looks a lot like the poor man's linearization. However, now there's this potential, which the potential is actually good. But there's also this first order term, which you should think is bad. Okay, so it's very difficult to understand solutions of this equation directly, precisely because of this bad first order term. So in particular, unlike for the poor man's linear problem, there is no known conserved energy for this equation. So the key observation, and this was actually first noted by Chandrasekhar. So this is a physical space analog of a fixed frequency observation of Chandrasekhar. One can apply a transformation to these two quantities, alpha and alpha bar, which schematically involve taking two derivatives in one of the two null directions, and the resulting quantities satisfy actually the Reggie-Wheeler equation, which first arose in that 1957 paper of Reggie and Wheeler. So Reggie-Wheeler, it looks similar to Minkowski. There's a potential which is good. It's a slightly different potential, but it's still good. But now that bad first order term has disappeared. So this solution, you should think, really is a lot like the poor man's linearization. And so those insights we gained in studying the poor man's linear problem mean we know how to show polynomial decay for these quantities P and P bar, and then by inverting these transformations for alpha and alpha bar. So that's approximately half of the story. The other half of the story involves controlling the gauge-dependent part of the solution. So again, remember, I always have one eye on the nonlinear problem. And for the nonlinear problem, it's important to control also this gauge-dependent part of the solution. So there's a hierarchical structure in the so once you know these quantities alpha and alpha bar, there's actually a hierarchical structure in the linearized Einstein equations, which allow one to control these quantities in turn. So maybe let me not say so much about that. So that controls L bigger or equal to 2 spherical harmonics. And remember, the L equals 0, 1 spherical harmonics is exactly where linearized Kerr lives. And so after subtracting a member of the linearized Kerr family, they one can easily show that the L equals 0, 1 spherical harmonics of the solution have to vanish. So that's very easy in linear theory. So I'm running out of time as predicted. So let me just re-emphasize some of the new nonlinear difficulties. So the very broad strategy is the same as the linear theory, in particular beginning with those gauge invariant quantity, those quantities which are gauge invariant in linear theory. In nonlinear theory, they're actually only almost gauge invariant. And then turn into what in linear theory is the gauge dependent part of the solution. So the gauge normalization has to be further refined due to nonlinear effects. So for example, recall I said in linear theory, one can tell a priori exactly what the location, the linear analog of the location of the event horizon will be. However, one of the big difficulties in this nonlinear setting is that we don't a priori know the location of the event horizon. And so this means the gauge has to be normalized a lot more carefully. Moreover, there are nonlinear terms now in the equations, and we require that they all decay at a sufficiently fast rate, and they will not decay at a sufficiently fast rate unless the gauge is normalized correctly. Then there's the issue of controlling nonlinear error terms. And again, we saw already in the discussion about stability of Minkowski space, how important it was to exploit very, very special structure of vacuum nonlinearities in the vacuum Einstein equations. There's also this difficulty of identifying the codimension 3 submanifold, which again in linear theory, this was explicit. And then of course, all of these difficulties coupled to one another. So as I say, if the gauge is not normalized correctly, the error terms will not decay at a fast enough rate. The way that the codimension 3 submanifold is identified relies on the fact that the nonlinear error terms decay sufficiently fast and so on. So let me I prepared a little bit more, but let me not go through that. Let me just jump to the following conjecture. So the next obvious question is what happens not just for Schwarzschild, but for Kerr. So I've stated here the conjecture for Kerr. This is exactly the analog of the theorem. That this is exactly the analog of the statement of the nonlinear theorem. But now for Kerr replacing Schwarzschild, and of course there's no need for a restriction to a codimension submanifold in this case. And recent years have seen a tremendous amount of progress on this problem, and I expect that in the not too distant future, we will actually see a full resolution of this problem for Kerr in the entire sub-extremal range. So thank you, and let me finish there.
Thank you. Thanks a lot. Thank you, Martin. That was great. So yeah, we have some time for questions. So if you want to ask a question, please raise your hand. Maybe I can kick off by asking the first question. So I was wondering when you were discussing how you have to restrict to this submanifold, codimension 3 submanifold, I was wondering, did you have to, where and how did you have to also consider, Schwarzschild modulo BMS shifting?
Yeah. Absolutely, yeah. So this is actually part of the, when I say that there's this whole infinite dimensional residual double null freedom, the BMS symmetry is actually part, the BMS freedom is a part of that double null freedom, exactly. Yeah.
Okay, so there is a somewhat larger submanifold, I suppose, which you could allow, and you would, in that case, you would allow solutions which are include, radiation, etc. You have killed those.
Oh, sorry. No. The only thing which is killed by that restriction is things which converge to Kerr with non-zero angular momentum.
How about, just L greater than or equal to 2 gravitational radiation that's radiated to null infinity?
Yeah, that's included in the.
That's included. So, and the conditions are consistent with the BMS.
Exactly.
Okay, I see.
Exactly.
Good.
Exactly.
All right. Other questions?
Achilles, how much time do we have for questions? Because I wanted to ask something about the nonlinear slides that were sketched.
Go ahead. We have at least 10 minutes.
Well, Martin, thank you very much for a beautiful talk.
Thank you.
Mind maybe elaborating a little bit more on what you had planned to elaborate on?
Thank you very much for that question. Yeah, so I could say just a few words about how these nonlinear difficulties are treated in practice. So, I mean, the first is this issue of identifying this codimension 3 submanifold. So the proof proceeds not just by considering one solution, but in fact by considering an entire 3-dimensional family of solutions. So one adds, you can think, so one begins with some initial data set D, and one adds to it the 3 solutions, the 3 initial data sets which describe the linearized Kerr solutions. So recall there was a 3-dimensional space. So we look at this entire 3-dimensional family, and the ultimate statement will be there is just one member of this family which converges to Schwarzschild. So the proof proceeds by evolving in retarded time u, and at each retarded time we throw away everything which has not radiated enough angular momentum. Okay, so we begin with this entire 3-parameter family, and then for each retarded time we start throwing away things which have not radiated enough angular momentum. And so angular momentum, it's identified by the L=1 mode of one of the curvature components. And so the idea is that in the limit, as this retarded time goes to infinity, everything will be thrown away except one thing, which has radiated all of its angular momentum. So there's a balancing act of what gets thrown away and what doesn't get thrown away. So implicit in this statement is a long time existence for things which also converge to Kerr. And because we only invoke this linear analysis around Schwarzschild, there's a limit to how many things, how much we can not throw away, how much we can throw away. But it's obviously desirable not to throw too much away. So there's a balancing act there. So then there's the issue of identifying the gauge and the black hole exterior. So this is again, so it for each retarded time u, there's actually there's actually 2 gauges which cover the past of that, the region of the space-time to the past of that retarded time. So one of those gauges corresponds to a near region, and the other corresponds to a far region, so, and they overlap. So it's as schematically depicted in this picture. So the near region is where the redshift effect is relevant. So we saw the redshift feature in the discussion of this poor man's linear problem, where it was our friend. It helped us prove decay. So here, from the backwards point of view, the redshift effect becomes a blue shift, and it makes things want to grow exponentially. So gauges which are only normalized to the in the far region typically will actually grow exponentially. Quantities will blow up exponentially because of this blue shift. So then there's the far region, and the far region is exactly where the null condition, which was so important in the stability of Minkowski space, is paramount. And it's to capture null condition, it's convenient to normalize the gauge differently in that far region. So in particular, it's this far gauge which is Bondi normalized. So they're defined by certain algebraic conditions on the Rishi coefficients. And as this retarded time goes to infinity, so this region becomes the black hole exterior, and it's thus these asymptotic algebraic relations which determine which find the black hole exterior. So then finally, there's the repeat in the linear analysis, which now everything is of course nonlinear. So as I say, the proof begins by the proof proper begins by considering the nonlinear analog of these quantities alpha and alpha bar, which in linear theory are gauge invariant and decouple. Now they're only almost gauge invariant, and they satisfy something which looks similar. However, now these equations are nonlinear, so there are nonlinear terms on the right-hand side to control. So there's a similar Chandrasekhar transformation to a good Reggie Wheeler type equation, which again is now nonlinear. And provided the nonlinearities are sufficiently well behaved, one can show polynomial decay for alpha and alpha bar. Then there's these remaining quantities, which in linear theory was the gauge-dependent part of the solution. And recall in linear theory, these were controlled by exploiting this hierarchical structure in the vacuum Einstein equations. Now this structure is only hierarchical to linear order. Again, there are nonlinearities. And again, in order to capture the null condition in these nonlinearities, it was convenient to normalize the gauge to infinity, as in the stability of Minkowski space. So that was all I was going to say. It would. I don't think I can say so much more in this setting.
Thank you very much. I had another question, but perhaps it's too much for time we have, or it's kind of in a slightly different direction. I mean, are there other questions in the chat, or?
No, you can go ahead, ask your question.
So I'm sorry, but I'm going to take us a little bit afield. Martin, I know you're an expert on this, so you know I've got you now in front of me, so I've got to just jump on the occasion. So the complications introduced by having matter fields in the stability, say, of Minkowski space have a certain form. I myself have worked more on black hole formation or trapped surface formation, so I have a little bit of a feeling of what those kind of, what brought about by the matter fields. But the stability problem for black holes is a whole different ballgame. And so I just wanted to hear your thoughts on to what extent are the complications of adding matter in the stability of Schwarzschild, say, to what extent do they really diverge from the usual complications one might have when one is thinking about stability of Minkowski or trapped surface formation or something like this?
So in generality, it's a bit difficult to answer, just purely because the answer depends very, very heavily on what type of matter. So, I mean, for example, you could consider coupling to the Maxwell equations. And of course, then there's not only Kerr nearby, but there's also Reiser-Nordström and Kerr-Newman. So the linear difficulties around Reiser-Nordström have been resolved by recently by Georgi. There's actually a very interesting problem, which you could also ask in vacuum, but it will be much more complicated in vacuum. So the problem is to understand what happens around extremal Reiser-Nordström. Okay, so around extremal Reiser-Nordström, we know that this is subject to the Aretakis instability. Moreover, we know that there'll be perturbations like sub-extremal Kerr and super-extremal Kerr. So actually, this formalism that we introduce here concerning the restricting to a full codimension hypersurface, I hope that that will be relevant in understanding what happens close to extremal Reiser-Nordström. So, for example, we include a conjecture about that in the introduction to our paper. So that's one very interesting feature of extremal of introducing coupling to Maxwell. Of course, you could ask that same question for extremal Kerr, but that's much more complicated. We don't even understand the poor man's problem around extremal Kerr yet.
What about other matter fields?
Other matter fields, I mean, it depends very much. So for example, you could consider Vlasov. That's a matter field which I like very much. Beyond difficulties which arise in around Minkowski space, for massive Vlasov, for example, the picture changes quite considerably. So remember that Kerr is something, it's a 2-parameter family or a 4-parameter family in this discussion. There should be, there's been constructed by, there's a construction already of an entire infinite dimensional family of stationary solutions of Einstein-Vlasov close to Schwarzschild. Moreover, one expects to see phenomena beyond what one sees here. So there are some works where people have exhibited, so in most of these problems, all of the decay mechanisms are a result of some form of dispersion. There are works for Einstein-Vlasov close to Schwarzschild, in which one sees different decay mechanisms, such as what's called phase mixing. And that seems very interesting. So that's a very good question.
Are people working on this now?
Possibly, yeah, possibly.
Yeah.
So there's been some works in the physics literature on phase mixing properties close to Schwarzschild, for example. Yeah.
But you think stability for Schwarzschild massive Vlasov is still very much distant?
Yeah, for example, without simplifying symmetry assumptions, that seems to be a very difficult problem, I think. I mean, there isn't even a complete characterization of all of the nearby stationary solutions. Oh,
so we don't actually know the classification, like there's no classification for these guys?
Correct, yeah, correct.
Oh, okay, thank you so much. I would love to, just keep listening to you, but
Thank you for the questions.
Thank you.
Yeah, that's great. Yeah, unfortunately though, we are a little over time now, so we should wrap it up. Let's thank Martin again. Thank you, virtual clapping and live. Thanks a lot. We hope to have you back soon live. We'll see everybody next week.
Thank you again for the invitation. Thanks.
Bye-bye.
Bye.